Hello everyone, welcome to lecture 19 on Mechanics and Materials 1. This is our fourth and last lecture on the topic bending. In this lecture we want to cover sections 6.5, 6.9 and 6.10 of the chapter 6 of the Hibbeler book. In particular we want to talk about unsymmetric bending, stress concentration and inelastic bending. In particular, the last two topics, stress concentration and inelastic loading, or in this case, inelastic bending, they are very similar to what we discussed when we talked about a torsion problem. So the first topic we want to talk about is the unsymmetric bending topic. Previously, we always assumed that the cross-sectional area was symmetric about an axis perpendicular to the neutral axis. And we also assume that the resultant internal moment acted along the neutral axis. So these are two examples of our particular assumptions here. You can clearly see that in both pictures, although the cross-section is not a square or let's say a standard shape, in both pictures you have axis of symmetry and you have a neutral axis with respect to which you can apply moment M. Now, when we talk about unsymmetric bending, you can break symmetry or the symmetry of the problem in either of the two ways. So you can think of cross-sections that do not have an axis of symmetry that we know in advance, basically. So if you have a, let's say, a cross-section which looks slightly more complicated than what we just have here, then that would be one type of problem that you would not have, basically the symmetry problem that we are dealing with. Alternatively, another type of unsymmetric problem for bending is that if the moment M is not exactly applied with respect to the z-axis. So for instance, if you think of a line here between z and y, and then you assume that you have a moment with respect to that axis. So what do we want to do then? Before we proceed, I want you to remember the flexure formula sigma equals minus my divided by I. So m is the internal moment, I is the moment of inertia. So the flexure formula in principle is still valid even if we talk about unsymmetric bending, but then we may need to use it in conjunction with the principle of superposition. I will clarify that in the next slide. So basically, as I mentioned, you can think of two types of unsymmetric problem for bending. One is if y-axis and z-axis, they are not the principal axis of the cross-section. So this is one type of problem where the bending problem would be unsymmetric, but this is a rather geometrical problem. We are not interested in that, but you can also solve that basically by solving for the principal axis first and then solve the bending problem. So here we assume that we know the principal axis for simplicity, otherwise you need to calculate them first. But alternatively, as I mentioned, we are more interested in a problem which looks like this one. So the cross-section itself, it could be still simple. It could be still a cross-section that we know, and for that cross-section, we know indeed what are the principal axis and symmetric axis. But then the moment itself is not symmetric. So here what we want to do is basically to use the principle of superposition and then elaborate on that bending problem with respect to each axis separately. Again, the point of departure is our flexure formula, sigma equals minus my divided by I. But what we want to do next is to split the system here as we did with superposition, into two systems. So if you think of the moment m, it has two components. It has mz, which is m cosine of the angle theta, and then you can have my, which is m times sinus of the angle theta. Now for each of the two problems, you can solve the bending problem separately, and you can add their solutions together in order to compute the solution for the whole system. The first system is very familiar to us. So if you have a cross section here and you apply a moment with respect to z-axis, this is exactly what we did before. So above the z-axis, you can see that the moment is compressive. So if y is positive, the moment is compressive, so it's negative basically. If y coordinate is negative, the stress is tensile, it's positive. And this is exactly why we had the minus sign previously. So basically what we want to do now is to use this formula, but maybe use it slightly more carefully for this type of problem. So stress equals minus, and then again, minus comes exactly from this observation that we had, minus moment with respect to z-axis divided by moment of inertia with respect to z-axis and distance times moment of bending moment times moment of inertia, but the distance is also distance from z-axis. So you can see clearly that here basically in this system, if you call it system 1, so this is stress from system 1, everything has to do with the z-axis. Moment with respect to the z-axis, moment of inertia with respect to the z-axis, and distance from the z-axis. And that would give you a stress distribution for system 1. And by the way, this stress itself is in the direction of the x, basically. Or in this case, because it has a minus, it's in the opposite direction. But, or let's say it's in the opposite direction in the upper part and in the same direction in the lower part. But the stress itself is a normal stress, and it's essentially sigma x. So what we want to do next is exactly to play the same game for this system. We want to calculate sigma or sigma x from system 2 here. Let's call this system 2 and let's call this system 1. So we already have stress from system 1. It's just here. So if we do exactly the same thing from system 2, then we would have the stress that we were looking for. As you can imagine, the flexure formula for the right system, for system 2, would formally follow the structure of the flexure formula that we have here. So here you can see that due to the moment with respect to y-axis, on this side you would have compressive stresses. So stress would be minus on that side, and on the other side stress is tensile, so it's plus. But you can also see that on the side where stress is compressive, actually z is less than 0, and on the side that stress is tensile, it's plus, z is also positive. This is different from what we had here. So basically that tells you that when you use the flexure formula, you no longer need the minus sign. So it comes with a plus sign. But now in this flexure formula, you have the moment with respect to y-axis divided by the moment of inertia with respect to y-axis times the distance from the y-axis, which is z coordinate. All right, so now that you have the answer for the stress from the first system and from the second system, all you need to do is to just add these two together and you get the stress formula. So this is exactly what we did in the discussion on the principle of superposition. All right, so long story short, if you have a cross-sectional area that itself is symmetric and you know the principal axis, but the moment is not symmetric, all you have to do is to compute the components of that moment and then use the principle of superposition to calculate the stress. So this would be basically our flexure formula for a problem like this. But the next thing we want to ask ourselves is, where is the neutral axis, or how we can extend the same discussion to the neutral axis position. So if you remember, we calculated the position of the neutral axis previously from equilibrium, and we do exactly the same thing. So we set equilibrium of forces, which would essentially be integral of forces over the area is 0, or otherwise integral of sigma dA equals 0. And if you insert the stress in this integral, I'm not going to do that, but you can clearly see that if you are on the centroid, so if y is 0 and z is 0, basically, this integral would be 0. So what happens is that, as before, the neutral axis passes through the centroid. So we don't know where the neutral axis is, so maybe this is the neutral axis. But we do know that it's passing through the centroid. We don't know the direction. So previously we did not have this problem. Previously, as soon as we learned that it is passing through the centroid, we knew that it was horizontal. We knew that the neutral axis was the same as basically the z-axis. That was the same axis where you would apply your moment with respect to. But now it turns out that the neutral axis is not necessarily the same axis that you apply your moment with respect to. So this is not necessarily the neutral axis. Okay, so how do we calculate that? Well, in order to calculate the direction of the neutral axis, all you have to do is to remember what was the definition of the neutral axis itself. So the neutral axis is called neutral axis because basically strain and alternatively stress is 0 on that axis. So all you have to do is to set stress equals 0 in your stress formula or in your flexure formula, and this would be your equation. So basically this is the equation for the neutral axis. It doesn't look like a line equation yet, but if we look at it more carefully, we can see the line equation in a moment. So what you need to do then is to just set this to 0, reorder the terms, and then you get the yellow term here. And then if you reorder the terms again, you would have an equation which looks like this. So this equation should remind you of something like y equals mx maybe plus b, where b is 0 and m is the slope of the line, except that now you are multiplying by z, but eventually this is y equals some sort of slope m times z. So this is indeed a line equation, which is the same as this one, which is the same as this one. So you already have the line equation for the neutral axis. But we want to understand how neutral axis is compared to the axis with respect to which you apply the moment. So is it, for instance, if you have this line, is this the neutral axis, or is this the neutral axis, or is it coinciding with that axis? We want to just take this to the next step. In order to do that, we need to just look at this formula a little more carefully. If you look at this, you see that the coefficient here, my divided by mz, is indeed tangent of the angle theta, which you can see from here. On the other hand, if you just look at the line equation, as I mentioned, this is nothing but the slope of the line. So if you assume your neutral axis is the red line shown here, the slope of the line would be tangent of alpha, and the alpha would be the angle we don't know yet. So the question is alpha equal theta or not? Is it larger than theta? Is it smaller than theta? This is what we want to answer. So this is your neutral axis equation. And if you want to compare that with the angle theta, then all you have to do is to look at this equation. So tangent alpha is equal this coefficient times tangent theta. So the first thing you can see is that it's not necessarily equal to theta. So alpha and theta are not necessarily equal unless Iz divided by Iy is 1, which tells you you have, for instance, a square cross section. So in order to better explain that, we look at a rectangular cross section here. So assume you have a rectangular cross section with the width b and height h. So in this case, Iz would be 1 over 12 bh cubed. Iy would be 1 over 12 hb cubed. So from these two, if you calculate Iz divided by Iy, it would be h divided by b to the power 2. So what does that mean? The first thing that it means is that if h and b are equal, which again it means it's a square basically, if h and b are equal, then this is 1, and tangent of alpha and theta are equal, and therefore alpha and theta are equal. But for instance, if Iz is larger than Iy, then alpha is larger than theta. So what does this mean? If you want, for instance, this cross section is longer in the y direction. So for this cross section, Iz is larger than Iy. So if you apply a moment with respect to this axis, the neutral axis would have an angle which is closer to the longer axis of the cross section. So neutral axis turns towards the longer side basically. All right, so this slide is sort of the whole discussion on the topic unsymmetric bending. This is your flexure formula. You know the neutral axis is passing through the centroid. This is the equation for the neutral axis, or this one if you want, and then the relation between the angles is here. If you want to also illustrate that, you can look at it like this. So basically what we did is to add the two stress distributions that we had here. So due to mz, we would have a stress distribution which looks like this, and due to my, we would have a stress distribution which looks like this. And now if you add these two together, you get a stress distribution which would look like this picture. And then obviously in this picture, you can see that your neutral axis would be somewhere here. So that is where the stress would be 0. And you can also imagine that, for instance, on this corner, you would have tensile stress from, let's say, system 1 added to tensile stress from system 2. So it's fully tensile stress. It's the maximum positive stress you can get. On the other hand, in the opposite corner, you get the maximum negative stress. So it's the maximum compression. So these are opposite to each other. And then on the other two corners, basically you get a combined effect. So you get positive stress or tensile stress from system 1 and compressive from system 2. Okay, so this slide is basically the unsymmetric bending and its illustration in a nutshell. What we want to do next is to solve an exercise together to better understand this. Exercise 1 of this lecture is similar to problem 615 on page 310 of the Hibbeler book. The rectangular cross-section shown in the figure is subjected to the bending moment of 12 kilonewton meter as shown. Determine the normal stress developed at each corner of the section and specify the orientation of the neutral axis. So what we want to do is basically to calculate the stress distribution and then identify the value of stress to evaluate the stress at each corner, C, D, E, and B. And we also want to find out the direction of the neutral axis, basically finding the angle alpha. So the first thing we want to do is to be a little more careful about this problem definition, because you should remember that the way that we define the axis direction in our previous formula was that y-axis was, let's say, the symmetric axis upwards here, and z-axis direction was like this. So basically, in view of that picture, if you look at this one, the 12 kilonewton meter moment, the moment that we have, is indeed applied like that. Okay, so you shouldn't be basically confused by that or think that the moment is applied somewhere here. If you look at the picture, this is the y-axis. This is the positive direction or plus direction for y-axis. This is the plus direction for the z-axis. And you can see that the moment is applied basically where theta is negative. Okay, so we measure theta from z direction when we developed our flexure formula. So basically what I mean here is that theta is minus 53.1. The value 53.1, obviously you just get it from the dimensions that are given here. So it's basically arctangent of 4 divided by 3. And then again with a minus sign because of the minus sign that you have there. All right, so once you have that, we should also remember that later when we calculate alpha, it would be in the same sense. Okay, so we defined alpha like this. So using the formula that we had previously, now you should remember that alpha may also lie in the same direction as theta. So you remember that tangent alpha is IZ divided by IY times tangent theta. So because the i's, the moment of inertia, are positive, theta and alpha would be on the same quarter basically. So if theta is negative, in this sense, if theta is negative, then alpha would also be negative. Okay, so the next thing we want to do is to just look at the flexure formula that we derived previously. So stress is minus mz divided by iz times the distance from z-axis plus moment with respect to y-axis divided by moment of inertia with respect to y-axis times distance with respect to y-axis, which is z. And then again, mz is m cosine theta, my is m sine theta. So what we want to do here is to calculate these values. So basically my, mz, iz, and iy, we need to calculate them. Once we have calculated them, then we take the coordinates of each corner and we can evaluate the stress at each corner. That's what we want to do. So from the theta that we have, cosine theta would be 3 over 5, sine theta would be minus 4 over 5, which again could be also observed from the dimensions given in the figure. And inserting these two values in the formulas that we had for mz and my, mz would be 7.2 kilonewton meter, my would be minus 9.6 kilonewton meter. And then again, having a minus for my, it makes sense because it would be downwards. All right, so now that you have the moments individually, what we want to do next is to calculate the moment of inertia Iy and the moment of inertia Iz. The moment of inertia for a rectangular cross-section is 1 over 12 bh cubed. And then depending on the direction, you would need to decide what is b and what is h. So if you want to calculate Iy, so in this case, 0.2 would be your h and 0.4 would be your b, because you calculate with respect to y-axis. So the formula would be 1 over 12, 0.4 times 0.2 to the power 3, and the moment of inertia with respect to y-axis would be 0.267 times 10 to minus 3 m to the power 4, meter to the power 4. The moment of inertia with respect to z-axis, this is more standard or similar to what we had done previously. So if you want it with respect to z-axis, then this is our b, and h is our height 0.4. So you would have 1 over 12 times 0.2 times 0.4 to the power 3, and iz would be 1.067 times 10 to the minus 3 m to the power 4, meter to the power 4. Okay, so at this point, we have all these ingredients from the flexure formula. All you have to do is to insert the coordinates. So you have already iz, mz here, and you have iy, my, and then inserting the coordinates of each corner, you would calculate the stress for each corner. So for corner B, the coordinates are plus 0.2 in the y direction and minus 0.1 in the z direction. So this is your point B. This is plus 0.2, and this is basically 0.1 in the negative direction. So you insert these two coordinates in this formula, and your stress at point B would be 2.25 megapascal. Then you do the same thing for point C. Now point C is here. For point C, both Z and Y coordinates are positive, and stress at C reads minus 4.95 megapascal. Then you do the same thing for point D. Now for point D, you can see that Z is positive, but Y is negative. Stress would be minus 2.25 megapascal, and eventually for point E, both YE and ZE are negative, and the stress at point E would be 4.95 megapascal. So if you collect all of this in one slide, this is what we have. Basically at B, we have 2.25. At D, you have minus 2.25, which shall be compared with the values at E and C. So here you would have plus 495, and at C you would have minus 4.95. So this is what we discussed before. Basically, the corners would have opposite signs but similar values. All right, so this is the first thing you wanted to do. You were asked to calculate the stresses at each corner, and these are the numbers. The last thing we want to do is to calculate the direction of the neutral axis. Again, we know it's going to pass through the centroid, but in order to calculate the direction, we define this angle alpha, and we use the formula or the relation we had: tangent alpha equals Iz divided by Iy times tangent theta. And since we have Iz and Iy, you just insert there, and you would get alpha equals minus 79.4 degrees. Which makes sense according to what we said. Basically, if you apply a moment in this direction or along this line, the neutral axis would move, or it tends to move toward the longer side, basically. So alpha is larger than, or in terms of absolute value, alpha is larger than theta. So basically, this is what you were asked to do. But if you want to also illustrate that, you can also illustrate it like this. The stress distribution would look like that. So on corner E, if you remember, we had plus 4.95. On corner C, we had minus 4.95. So that basically tells you that you have a fully tensile stress here and a fully compressive stress here. On D, you have a tensile stress or effective tensile stress. On D, you have an effective compressive stress. All right, so that was all for this example. So the next topic we want to talk about is stress concentration. Now, stress concentration under bending is very similar to the discussion that we had also previously under torsion and under axial loading. So stress concentration itself, it occurs due to geometrical imperfections. And a good example of a geometrical imperfection is changes of cross-sectional area. So you can imagine if instead of just having a uniform cross-section, you have a member which looks like this or this or this one, here something more interesting will happen. So close to the geometrical imperfections, the stress will increase or it will concentrate. Recall that the flexure formula reads sigma equals minus my divided by I. And it basically gives you a linear stress distribution if there is no stress concentration. Also, it tells you that the maximum stress would be mc divided by I. Again, if there is no stress concentration. So this is valid for uniform members. But what happens now is that the actual stress you get due to stress concentration is larger than that. So you need to basically multiply this by a factor k, the stress concentration factor, to get the actual maximum stress. So basically this would be your actual maximum stress, and this would be your maximum stress if we did not have a geometrical imperfection. And then the factor in between, the stress concentration factor, it's always larger than 1. For instance, if we look at a rectangular cross section here, assuming that the dimension here is b and height is h. Now, if you look at this formula that we have here, and you look at c divided by I, you can see that this relation is h over 2 divided by 1 over 12 bh cubed, which basically tells you that c divided by I, c over I, is proportional to 1 over height squared. So why is that important? If you think that height here in the larger section is capital H, and in the smaller section is, let's say, small h, the stress here would be larger than the stress here. And I'm talking about the uniform part. I'm not yet talking about the concentrated part. If you are talking only about the uniform part yet. But basically, this formula tells you that your c divided by I is proportional to 1 over height squared, telling you that if h is smaller, you get a larger stress. So why does that matter? Basically, this tells you that the maximum normal stress occurs at the section with the smallest cross-sectional area. In other words, if you look at these three pictures, the stress will occur basically at the sections where you have the smallest cross-section. And that is where you need to look into this formula. So you calculate this part, which you know it would be naturally larger than anywhere else, and then also you multiply that by the stress concentration factor. So what you get is something like this. Again, the stress distribution that you would see here is now the actual stress. So it's not linear because you have the stress concentration factor. But if it was the linear function, it would have been something like this. But importantly, you see that you are looking at the stress distribution basically on the smaller part. Okay, so we are not looking at this one because we know whatever this distribution is smaller to what you have here. So the critical area would be this one. Okay, the next thing that you need to do basically is to calculate the stress concentration factor. K, the stress concentration factor you can calculate from the graphs here or from tables. And then again, these graphs are very similar to what we had before. They are not identical. So for a bending problem, tables are different from a torsion problem. They are different from axial loading problem. But in this case, these are the graphs you have, and R is again the radius here, the fillet or the notch radius here, and W over H is the ratio of the larger height over the smaller height. And you can imagine if this ratio gets larger, you would get larger stress concentration factors. And if this ratio is 1, basically you would have a uniform cross-sectional area, so no concentration factor. If R goes to 0, you can see that stress concentration factor increases rapidly. So basically that tells you that you need to avoid sharp corners. Similar conclusions you can also make from the right graph here. So what we do next is to look at this problem with an exercise together. Exercise 2 of this lecture is similar to problem 620 on page 332 of the book. The bar shown in the figure is subjected to a bending moment of 5 kilonewton meter and is made of steel with yield stress of 500 megapascal. Determine the maximum normal stress developed in the bar. So you have the bar here, the cross-sectional area, as you can see, it's not uniform. So you would have a stress concentration in the vicinity of the area here. So what you need to do is to calculate the maximum stress here in the smaller part, then multiply that by the stress concentration factor to get the maximum stress. So here is the graph for the stress concentration factor with respect to the dimensions of the problem. So in the horizontal axis, we have R over H. In this problem, R is 16 millimeters. H is the height of the smaller part, so that's 80 millimeters. You can actually see the dimension H shown in the figure. So R over H is 0.2. W over H, on the other hand, is 120 divided by 80, which is 1.5. So 120, 80. Now, if you intersect the line with W over H of 1.5, if you intersect that line with the line of R over H 0.2, you get the stress concentration factor of 1.45. Now, once you have the stress concentration factor, what you need to do is to just multiply that by mc divided by I. Now, the moment is 5 kilonewton meter, so 5 times 10 to the power 3. C is the maximum distance from the neutral axis, but this is the maximum distance for the small part. Remember that we are looking at the more critical section, which is the smaller part. So that would be 40 millimeters or 0.04. The moment of inertia is 1 over 12 bh cubed. And in this case, b is the thickness, h is the height of the, again, smaller part. And if you calculate all of this, you get 234. You multiply that by 1.45, you get the stress of 340. Or more specifically, this is 340 megapascal. Now, if you remember, the yield stress was 500 megapascals, so you can do a quick check if the material is still in the elastic range and it holds. So basically, the solution is valid. Now, the reason we need to do this check is that you need to remember when we derive this formula, the flexure formula, at some point, we use the relation sigma equals E epsilon. So this was our elastic assumption. Okay, so basically everything that we say here, we have a stress concentration factor and everything, but we are still within the elastic regime. So if you wanted to draw the stress distribution for the uniform area, so it would be an area far away from the crucial area here. If you draw the stress distribution there, you will expect a linear stress distribution. And this is as we expected before. So you would get compressive stresses on top and tensile stresses at the bottom. But then if you look at the area close to the critical section, or at the critical section, what you can see is that your maximum stress would be 340 instead of 234, but also the distribution is no longer linear as before. It's now, let's say, a nonlinear distribution. The last topic that we want to discuss in this lecture is inelastic bending. So imagine our usual bending problem, and maybe for simplicity with a rectangular cross section. The strain distribution in this type of problems is linear. But the linear distribution of the strain is a geometrical definition. So this is basically what we had at the beginning. This is where we started from, and this comes from the geometrical assumptions that are associated with this type of problem. So we assume there is a neutral axis, and then we had a linear strain distribution as given here. Now, if you want to see the stress distribution, previously we assumed that we were always within the elastic range. And within the elastic range, because strain and stress are proportional, linear strain also meant linear stress. So previously, the stress was also linear because the strains were linear. So now the question is, if we increase that limit, then we come to a point that the material yields. So we come to the yield stress sigma y at the yield strain epsilon y basically. So we want to know how to calculate the relationship between moment and deformation basically if you have an inelastic bending. And then again, the topic that we are dealing with here is very similar to our discussion when we had discussed this for torsion problems. For simplicity, you can always imagine that we are talking about a rectangular cross-section. The first thing we want to ask ourselves is, what is the maximum elastic moment? So what's the maximum moment I can apply and the member still remains within the elastic regime? So this is basically the maximum point. This is as far as you can come, and it would be still elastic. So in order to do that, we begin with our moment formula. So you remember that we calculate the moment by integrating distance times force over the area, and incremental force is stress times incremental area. So this formula itself is generic. It doesn't know anything about stress yet. So the stress could be linear or not. But if we talk about elastic problems, then it means we assume it's linear. So we have done this basically. So we assume that strain and stress, they were both linear because we talked about elastic problems. So if you remember, we also had this relation that stress was minus y divided by c sigma max, for instance. Okay, so we assumed a linear distribution of stress, and then if you go through the steps as we did previously, you would end up with the so-called flexure formula. But now when you want to calculate maximum elastic, it means that the maximum stress in our flexure formula should be the same as the yield stress, sigma y. So you insert sigma y instead of sigma max, and you would get the maximum elastic moment, which is equal sigma y divided by c times I. So this is the maximum elastic moment. This is the maximum moment you can apply, and still you would be within the elastic regime. So after that, now if we exceed the maximum elastic moment, what happens is that we enter into this zone of elastoplastic regime, where somewhere inside the material where the stresses are not yet large enough, we will have an elastic response, so we call that elastic core, and then outer or in the outside area, the stresses are already exceeding that, or the strains are basically exceeding the epsilon y, which means the stresses are all equal to sigma y. So again, if you assume that you have a strain distribution like this, strain distribution is still linear. So strain distribution is linear, but somewhere you would reach the strain epsilon y, and if the strain is larger than epsilon y, in those areas, the stress would be just constant sigma y. So now if you want to calculate the elastoplastic moment, you can do it again using exactly the same formula that we had before, but now you need to split the area over two parts, the elastic core and then the, let's say, the surrounding plastic regime or plastic ring if you want. So the elastoplastic moment is then therefore always larger equal than elastic moment itself, but it cannot go to infinity, obviously. So at some point you would have a complete plastic zone everywhere, and that would be your maximum moment or maximum plastic moment, which we call MPL. So basically what it means is that if you keep increasing the moment, then all the points would be experiencing a strain that is larger than the yield stress eventually. And what that means is that you would have the moment, which we call plastic moment, and that's the maximum plastic moment. That's the maximum moment you can apply to this member. So what does that mean? It means if you want to calculate that moment M, all you have to do is to assume that the stress in the formula in the integral is just the yield stress itself. You should also be careful with the signs. So in the upper part, you would get compressive stress. So maybe you want to just call it minus sigma y. And in the lower part, you would have plus sigma y. So in that sense, you would get a compressive force, let's call it C, and then a tensile force T, which are equal in magnitudes but different signs. And if you just multiply them by their effective distance, you can eventually calculate the moment. Okay, again, the important thing is that here we talk about the yield stress, but you should remember that in the upper part the yield stress is compressive, in the lower part is tensile. So if you do that, you just insert it as sigma y here, then you would have the integral from minus h over 2 up to h over 2. But as I mentioned, if you are not careful with the sign, basically you may want to just integrate twice of half the area. So you integrate from 0 up to h over 2, and then you multiply that by 2. And by doing that, you automatically account for the sign, so you make sure that they don't cancel each other, so you don't get 0. And if you do the integration, you would get the formula 3 over 2 sigma y divided by c times the moment of inertia I. Now, this would be your maximum plastic moment or maximum moment. If you remember, this part itself, this was maximum elastic moment. So what you can learn from this is that the maximum plastic moment is 50%, is exactly 50% larger than the maximum elastic moment. To summarize, if we have an inelastic bending, and then again, you can always assume that you're talking, for instance, about a rectangular cross-section for simplicity, the elastic regime or the maximum elastic moment would be sigma y divided by c times I. And that means if your moment is smaller than maximum elastic moment, then you are within the elastic regime. If your moment reaches the plastic moment, 3 over 2 sigma y divided by c times I, then you are in the plastic zone. That's the maximum moment that you can apply. You cannot exceed this. So maximum plastic moment is actually the maximum moment. And anywhere between the two, between the maximum elastic moment and maximum plastic moment, you would have a moment which results in an elastoplastic behavior. So you would always have some parts close to the center which would be elastic, and then some parts further which are, or some parts farther from the center which are plastic. There is only one last thing that I need to mention, is that remember when we calculated the neutral axis, we also calculated the location of the neutral axis from the equilibrium equation. And again, if you remember, in that equilibrium equation, we used the relation, the linear stress relation for the stress. So we calculated the neutral axis for linear stress distribution. Now, if you enter into this inelastic zone, and especially if you have unsymmetric cross sections, what can happen is that the position of the neutral axis can also change, because the relation here would change. So you remember, basically the consequence of using this relation was later that something like integral of y dA was 0, and this integral is what we used to conclude that the neutral axis was coinciding with the centroid. So in that case, you may want to now be more careful if you have an unsymmetric cross section and if you have inelastic bending, something more complicated can come up, and you need to pay attention to that. So that is what we want to do in the next exercise together. Exercise 3 and the last exercise of today's lecture is similar to problem 622 on page 346 of the book. A beam with the dimensions shown in the figure is made of an elastic, perfectly plastic material having a tensile and compressive yield stress of 250 megapascal. Determine the maximum plastic moment, or the plastic moment that can be resisted by the beam. The beam cross section is given here with the dimensions that you can see. So recall that when we calculated the position of the neutral axis, we used the equilibrium equation. Now, in that equilibrium equation, we use the linear distribution for stresses, which came from the linear distribution of the strains, and that was only valid if we had elastic relationship between stress and strain. But this relation no longer holds, so we cannot use that. And basically that means the conclusion we had previously, it doesn't hold. So if we knew previously that the neutral axis was here, it doesn't mean that it must be there also now. So what we need to do is to calculate the position of the neutral axis first with respect to the cross-section that we have for a plastic loading, for a fully plastic loading, and then based on the position of the neutral axis, we can calculate the maximum moment itself. So the equilibrium equation that we had, it still holds. So it's still integral of forces is 0 and integral of forces is integral of stress dA. The difference though is now that when you want to insert stresses here, the stresses are not having a linear relationship or a linear distribution. They are all sigma y. They are all yield stress. Because for instance, we are thinking of a case where you have fully compressive stresses above a neutral axis. So assuming that this is your neutral axis, we are assuming that everywhere above the neutral axis is fully compressible and it is at the yield stress, and then everywhere below it is tensile. So for instance, if the neutral axis is here, we assume that you have the forces like this. So T stands for basically the integral of all the tensile forces below the neutral axis. C1 is the integral of all the compressive forces, but only in the portion between the neutral axis and the larger part on top. And C2 is the integral of all compressive forces on the upper part of the T cross section. So if you pay attention, what I did, I assumed that the neutral axis was somewhere here. So I already implicitly assume that the distance from the bottom for the neutral axis is less than 120 millimeters. Obviously, we can calculate this, and if we end up with a distance that is not smaller than 120, it means we had a wrong assumption, and then we need to reevaluate this. And that would mean that the neutral axis would be somewhere here. But as we will see, this assumption is actually correct. All right, so your equilibrium equation now simplifies because you can cancel all the yield stresses, and it would be simply this. Now, AT is again the area below the neutral axis. This is your AT. This is the area at which we have tension, and D is the distance we are looking for, by the way. So we don't know what D is, but that area would be 15 millimeters times D. Now, if this is the neutral axis, the area of C1 or AC1 is again 15 millimeters times 120 minus D. And then the area of the upper part is simply 100 millimeters times 15 millimeters. And if you set that to 0, because it's your equilibrium, then you would get D equals 110 millimeters, which is indeed less than 120. So basically your neutral axis would be somewhere here, fairly close to the upper part, but 110 millimeters from the bottom. All right, now that you know the position of the neutral axis, the first thing you can do is to calculate the forces that we talked about. So you know the force T is the area AT times the yield stress. So the yield stress is 250 megapascal, and the area is 15 millimeters times 110 millimeters. So your T would be 412 and a half. Then you do the same thing for C1. This is sigma Y, yield stress, times the area of that little part. And then again, this is 120 minus 110 millimeters, which is 10 millimeters. So you get C1, that is the overall compressive force on that little area. And then eventually the overall compressive force on this area would be, again, sigma Y times the area, that is 375 kilonewton. And you can imagine that if I add this up, or basically this one with a plus, these two with a minus, because you have the signs, they should also satisfy the equilibrium equations. And they do. So the equilibrium of forces is still valid. Okay, so now that we have this, all you need to do is to calculate the moment due to these forces. So you know you have a force T, and then they have uniform distributions. So basically, if you have a force T, you know it's going to be at the center of that little part. So if this is 15 millimeters and this is 110, your effective force T would be at the center of that rectangle. So basically, you know the distances of each of these forces from the neutral axis, and all you have to do is to calculate the moment. And basically, that's what we are going to do. So as I mentioned, you can imagine that this is your distance d. So your effective force T is at the center. So with respect to the neutral axis, which would be on top here, the distance would be d divided by 2. So you would get T times d over 2. That is the moment that you get due to T, due to the tensile part of the force. Then you also add the moment that you get due to C1, and you add the moment that you get due to C2, and you can see that all of them are causing the same direction of moment. So you basically just add them up, and you can get the maximum plastic moment. So if you have the cross section here, for instance, and this is your neutral axis, for the part here, for the little part here, then the distance, you can imagine this would be half of 120 minus 110, which is d here. So this is what you see. And then c is the force you multiply. Then you do a similar thing for the larger part, but now you also add half of its own thickness. Okay, so you do this, and then you get the maximum plastic moment equals 29.4 kilonewton meters. And then again, I just mentioned this again, if you think of the T, and if this is the neutral axis here at the distance d, you can imagine that the distance that you are looking for here is half of 15 millimeters plus, in this case, 10, which is 120 minus d. Okay, so you can recognize these numbers here. All right, so this is your maximum plastic moment that you can have on this cross section. So this was our fourth and last lecture on the topic bending. We covered sections 6.5, 6.9, and 6.10 of the book. In particular, we talked about unsymmetric bending, stress concentration, and inelastic bending. So we are done with chapter 6 of the book. What we want to do in the next lecture, in lecture 20 basically, is to talk about a consequence of bending, and it's that we want to talk about deflection. And that would be the discussion on chapter 12 of the book. I'll catch you in the next one.